Now let us go into a brief history about the Fourier series. That is, the French mathematician Jean-Baptiste Joseph Fourier used the Fourier series first as a technique to model the heat conduction and temperature distribution over a body, which was not quite revolutionary at that time, but upon further analysis and further research about his model or topic, the Fourier series proved to be very much useful for signal analysis that we are using today in order to design various types of digital signal processing units, the digital filters, and likewise other devices. Now in our case, the Fourier series is used to apply to the periodic signal. That means if a signal is periodic in nature, we can use the Fourier series in order to convert the signal from time domain to frequency domain. Now, in broad sense, what does a Fourier series mean, or how can we define a Fourier series? So, Fourier series let me switch to another color. Fourier series is a tool by using which we may decompose any periodic signal to a number of sinusoids with various harmonics. Now, what does this essentially mean? It means that if a signal, say for x of t, which is periodic in nature, this signal can be expanded or decomposed into a number of sinusoids. By sinusoids I mean sines and cosine functions with various frequency components. It will become much more clear if we see the mathematical expression where x of t can be written as a0 plus a1 cosine of omega naught t plus a2 cosine of 2 omega naught t plus a3 cosine of 3 omega naught t, and this goes on, so and so. Plus there will be some other components of sine functions, that is sine of omega naught t plus b2 sine of 2 omega naught t, and so on and so forth. Now here the signal x of t, it is expanded such that there are number of cosine components, cosine functions and sine functions, and with increasing term of frequency. We all know that omega naught is the angular frequency, and here a0, a1, a2, a3 and likewise b1, b2 and so on so are called the Fourier coefficients that weights the function and is regarded to be the amplitude of the respective sinusoids. Now the beauty of Fourier series is that any signal that you can imagine practically can be represented by a summation of sines and cosines. Say for instance, if x of t is this type of function, where this is the time axis and this is the amplitude, let us say if this signal is something like this, this can also be expanded into number of sines and cosines using the Fourier series, and it has made the work of an engineer very much lighter and very much unimpeded in the regard of signal analysis. Now coming back to the initial expression, if I denote it as A1, here A1 can be implied as such, where x of t, the periodic function that we have defined, can be written as A0 plus a running summation of n equals 1 to infinity of an cosine of n omega naught t plus bn sine of n omega naught t. It means that this crazy equation can be complicated to write, and so we may simplify it as like this one. Now here, if you can see that A0 is devoid of any sine and cosine function, and it is called the DC weight of the Fourier series, and this does not depend on any sine or cosine functions, whereas an and bn will always depend on the nature of the sine and cosine functions. Now the series which is shown over here is called the trigonometric form of the Fourier series, and this series also has an exponential form. The exponential form can be written as x of t equals a running sum where n goes from minus infinity to infinity, f of n, which is the Fourier coefficient, and the exponent, that is e to the power jn omega naught t. Here n is the harmonic or the frequency component, and to determine various harmonics, and n must always be an integer number. Omega naught is the angular frequency and t is our time. Now, ladies and gentlemen, a question may arise in ourselves or in our mind that how these two forms, I mean this one and this one, are analogous. So we shall try and see the analogy between these two expansions, and let's start with the exponential form, that is x of t equals summation of n tends to minus infinity to infinity f of n exponent of jn omega naught t. Now, if you know the nature of running sum, this can be expanded as follows, where f naught, when the value of n is 0, we get fn as f naught, and in anything, if we put exp j 0 omega naught t, then this value becomes 0. So e to the power this value becomes 0 and e to the power 0 becomes 1. Hence, we get a DC component like that of the trigonometric Fourier series, that is f0. And upon further expansion, we get f1 exp, that means the exponent of j omega naught t, where the value of n is 1, and consequently f2 exponent of j to omega naught t plus f3 j3 omega naught t, and this will go until positive infinity. And as for the negative infinity, we can also write f of minus 1, where n equals -1. As you can see in the running sum, n runs from minus infinity to infinity. So unlike that of the trigonometric series, we should not consider n from 1 to infinity. Rather, we shall consider the negative numbers as well. So f -1 is the Fourier coefficient, and exponent becomes exp of minus j omega naught t, f of -2 minus j omega naught t plus f of -3 e to the power minus j 3 omega naught t, and this will go on until minus infinity. Now, ladies and gentlemen, let us recapitulate the Euler relation which says that e to the power j theta can be written as cosine of theta plus j sine of theta, and consequently e to the power minus j theta can also be written as cosine of theta minus j sine of theta. And in our case, theta equals omega naught t. Okay, now going back to this relation, over here, we can replace the value of e to the power j omega t and consequently e to the power j 2 omega naught t and so on, so as under, where x of t becomes f0 plus f1 cosine of omega naught t plus j sine of omega naught t plus f2 cosine of 2 omega naught t plus j sine of 2 omega naught t, and this goes on. And similarly, for the negative terms, we write f of -1 cos of omega naught t minus j sine of omega naught t. Here, as since j is negative, so we are using this formula, and f of -2 shall become cos of 2 omega naught t minus j sine of 2 omega naught t, and this shall so on, so go on until infinity. Now let us factor out cosine of omega t, sine of omega t from these two terms, and the equation becomes something like this: f0 plus the summation of f1 plus f of -1 cosine of omega t plus f2 plus f of -2 cos of 2 omega naught t, and this go on so forth, plus j f1 minus f of -1 sine of omega naught t plus j f2 minus f of minus 2 sine of 2 omega naught t, and this goes so forth. If you observe carefully, this expression can be written f naught as it is, and this one can be written as a running sum of n equals 1 to infinity, where the coefficients become f of n plus f of minus n cosine of n omega naught t plus j f of n minus f of minus n sine of n omega naught t. Now it must be said that the initial range was minus infinity to infinity, but now the range has become n from 1 to infinity, which is somewhat analogous to the trigonometric series. And if we write the trigonometric series, which was x of t equals a naught, which runs from n equals 1 to infinity an cos of n omega naught t plus bn n sine omega naught t. So in both the cases we see there is a DC component. The sum runs from 1 to infinity, and an is analogous to this term fn plus f of minus n, and similarly bn is analogous to this term. So I hope you understand how the exponential form of Fourier series comes from the trigonometric form of Fourier series. Now, we shall not be bothered about the trigonometric Fourier series for the rest of the course. We shall only be working with the exponential form of Fourier series, which is, in short, x of t summation of n, which goes from minus infinity to infinity, f of n exp, that is e to the power j n omega naught t, and for further derivations this can be written as x of t summation k equals minus infinity to infinity c of k e to the power j 2 pi f naught k of t. Here nothing has changed essentially. The term n is replaced by the term k. F of n is written as c of k, and exp, the e to the power, which is the natural logarithm, it will remain as same. What have changed is that the angular frequency omega naught, it is written as 2 pi f naught. That is omega naught equal to 2 pi f naught, which makes f naught our linear frequency. N is replaced by k as seen, and the time remains same. Now, ladies and gentlemen, we shall go to find the Fourier coefficient, that is c of k, using the mathematical techniques. So, derivation of coefficients of the Fourier series. Now suppose x of t is a periodic continuous function. I cannot stress enough that the function must be periodic. Otherwise, Fourier series might not work in this regard. So, as we have seen before, x of t can be decomposed as k from minus infinity to infinity as a running sum ck e to the power j 2 pi f naught k of t. Let us denote it as a2, where k equals 0, plus minus 1, plus minus 2, and so on. So that means k are both positive and negative integers, but k must be an integer. Now if that is the case, we know that the linear frequency is equal to f naught, and from that we can very easily determine the time period, that is t of p, to be equal to 1 over f naught, and the angular frequency to be 2 pi f naught, otherwise can be said as omega naught. Now, as I have said before, our target is to find c of k, and in order to do so, we must multiply both sides of a2 is by the term e to the power minus j 2 pi f naught L of t, where L is similar to k and can be any integers. Hence, the expression of a2 will become x of t e to the power minus j 2 pi L f naught t. Remember, we are multiplying both sides by this term, equals e to the power minus j 2 pi f naught L of t. And the remaining term remains as it is, which is a running sum of k, which goes from minus infinity to infinity, ck exp of j 2 pi f naught t. Let us mark this as equation B1. Now, let us take the integral with respect to time over the time period Tp. And in doing so, the expression becomes T naught to T naught plus Tp, where T naught is any arbitrary value. What we are concerned is the integral runs over from 0 to Tp or T naught to T naught plus Tp, which is essentially the same case, x of t e to the power minus j 2 pi L f naught t dt, which equals T naught from T naught to T naught plus P e to the power minus j 2 pi f naught L of t summation of k goes from minus infinity to infinity c of k e to the power j 2 pi k f naught t dt. Now let us be concerned with the right hand side of the equation for this time, and the right hand side can be further simplified as summation of minus infinity to infinity c of k t naught to t naught plus t of p e to the power j 2 pi f naught k minus L of t dt. See, here I've done nothing. The property of running sum and integration is such that they are both interchangeable, and anyone we can do first, it does not hamper the result. And since c of k does not depend upon this integral value, that is, there are no terms of time in ck, so it can be brought out of the integrand. And the rest of the term here, e to the power minus j 2 pi f naught, remains as it is, and by the property of exponents we can subtract the value of minus j 2 pi f naught L of t from the value of j 2 pi k f naught t, and it is written as this. And we have factored out j 2 pi f naught t and dt. Now this can be further simplified as under, where this remains the same, k goes from minus infinity to infinity c of k, and let us suppose, say, this term is written as x of a, because this is quite a crazy term and writing it numerous times will be time consuming. Now we shall be bothered about x of a. Now x sub a, or x of a, can be written as, or x of a essentially is t naught, that goes from t naught to t naught plus tp e to the power j 2 pi f naught k minus L t dt, and this is and this can be written as t naught to t naught plus tp cos of 2 pi f naught k minus L t dt plus j I'm sorry for the inconvenience, and j integral of t naught to t naught plus tp sine of 2 pi f naught k minus L t dt. I say what, let us write it in another page for clarity. X of a equals I'm writing the previous equation, 2 pi f naught k minus L t dt, integration of t naught to t naught plus tp sine of 2 pi